Okay, it's very nice to have this opportunity to give this series of lectures. So I have 3 lectures on the topics here. Let me just tell you briefly what is the idea. So there has been recently a sort of a mini explosion in the study of 3-dimensional, 2 plus 1 dimensional, or I'll be using the Euclidean terminology, 3-dimensional conformal field theories and 3-dimensional quantum field theories. So I wanted to start from some background to why 3 dimensions is so rich, why we can construct so many interesting conformal field theories, and there are all these dualities that you may have heard about. So the goal of my main 3 lectures is to cover some foundational topics like discrete anomalies on the lattice, discrete anomalies in the continuum. These are like foundational basic topics in theoretical physics that you need to know in general, and you need to know them in particular if you want to understand the origin of these 3-dimensional conformal field theories, which are called non-Landau-Ginzburg theories. So you need to understand these topics if you want to understand the origin of these things and their physical implications for high-energy physics and condensed matter physics. Also, these topics are a little bit outside of the beaten track for people who are educated in high-energy physics. Like, I mean, this is not something you typically study in courses on quantum field theory. And so the reason I decided to present this background is because it has many ideas that you may have never seen. And some of them seem to me like they could be actually useful for various things that you might be doing. In particular, many ideas here may have some interesting ramifications for Hamiltonian truncation and for various other questions that you're studying when you do like numerical bootstrap. The construction of the 3-dimensional CFTs is obviously of a lot of importance for the bootstrap program because you more or less need to know what to aim at. You need to know which CFTs are interesting. So I'll talk about QED in 3 dimensions and its miraculous properties that have been recently uncovered. I'll be talking about some other similar field theories in 3 dimensions and some very surprising properties. So you need to know more or less what to aim at. And then, independently of that development, completely independently and logically distinct, tomorrow morning there will be 1 hour lecture, I guess 1 hour and 15 minutes lecture about the TT, what people call the TT bar deformation. So that is particularly interesting again for Hamiltonian truncation, but also for the S matrix bootstrap. It teaches, and also it's a very interesting development if you want to understand what quantum field theory is, what is effective field theory, and stuff like that. So this is completely independent, based on some work. It will be mostly basic stuff that is already in the literature, but I'll present it in a way that's unpublished yet. Okay, so, and also please stop me at any moment, right? I mean, I should take questions, and just stop me whenever there is anything that comes up. Along the way, I'll be giving lots of problems, some of which are almost trivial, some of which require some meditation. And so it would be nice if you see me during the break or in the evening and you ask questions, and if you are not able to progress on one of the problems, we could try to discuss it. I may be able to eventually convert these things to PDF, but I can't promise. Okay, so we'll start from the first topic. The first topic would seem to be weird. It's the first topic is what's called the Perron-Frobenius theorem. It's just a simple thing from linear algebra that is extremely important for the applications in physics. And I think that maybe most of you who took linear algebra courses did not study that particular topic, so I'll cover it in some detail. Does anybody happens to know what it is? So nobody knows what it is. That was also true for me last year. So, but then I learned to appreciate it, and it appeared in many in many papers that I wrote over the last year. It's a very surprising result. So, so the first result that I'm going to present it in a little bit of detail because you'll see some of these things that appear in the mathematical proof have a very interesting physical interpretation. That's why instead of just giving you the theorem and then running with it, I'm going to cover the proof. So let A be an n by n matrix. And I will use this notation, A bigger than 0, to mean that all the entries of the matrix, all of them, are strictly bigger than 0. It's a basis-dependent statement. But let's suppose that such a basis exists. So the statement that I would like to prove first is the following surprising statement. There exists a real eigenvalue, lambda. So this matrix may not even be diagonalizable. But the statement is that there exists an eigenvalue lambda, which is real. And it's bigger in absolute value than all the other eigenvalues. So the biggest eigenvalue in absolute value is real. That's what it says. And it has multiplicity 1. So it's non-degenerate. There is well, as you may remember, there is something that's called algebraic multiplicity and geometric multiplicity, and both of them are 1. So I want, okay. This is the first part of the statement. This is the simpler version of the theorem by Perron, and what we'll actually need to study applications for physics would be a slight generalization. So this is the first statement. And the second statement is that the eigenvector corresponding to lambda, which I'll call psi, is also positive. Okay, so that means that in this basis, all the entries are strictly positive. This will be extremely crucial to establish the existence of a non-degenerate ground state in some quantum field theories. You'll see how that plays out. And A, of course, will be the Hamiltonian. Okay, so let me just take you through the idea of how to prove that. If there are any questions about the statement, just let me know. You can. So there is a small trick that we will employ. And the trick is that given such a matrix A, suppose you have two vectors, theta and psi, that satisfy, well, let's call this a particular one psi lambda, so that we don't get confused. So the first trick is that you take two vectors that satisfy the weak inequality, meaning that every component of theta is bigger or equal than any component of psi, but they're not the same. So you have to. So they're not the same vector, so you have to say at least one component of theta is strictly bigger. Okay. So then, what we will need to use is that there exists a small positive. There exists some positive epsilon for which this is true. So this is now a strict inequality. So there exists some positive epsilon where this is true. Yeah.
This is like finite dimensions?
Yeah. This is an n by n matrix. I should have, before I jump into describing the proof, I should have given some credit. So this topic has been first developed by Lieb and collaborators, Elliot Lieb from Princeton and collaborators. Then Hastings and various people, and then Affleck and so on. So these are the people that, this is new. This is new. This appeared probably for the first time last year. And this has been a topic, the search for conformal field theories in 3 dimensions has been a hot topic in condensed matter physics for over a decade, But using this more coherent picture, it's also something that's kind of new. People are working on these things nowadays, and and this story is started by Smirnov and Zamolodchikov, and there have been quite a few papers on it over the last couple of days, even the last couple of days or the last couple of weeks, as if you're following the archive. Okay. Okay, so this trick is very easy to. It's very easy to see that this is true. That's trivial because, you just apply the inequality term by term for each component, and since at least one term in theta is strictly bigger than some term in psi, then the weak inequality turns into a strong inequality. So that's obvious, but because that is true, then you can also arrange for small enough epsilon that it would still remain true. Because if two vectors satisfy strict inequality, you can multiply one by a tiny bit so that the strict inequality remains true. So the proof is that this is obvious, and then this follows. So that's it. You can fill the dots. Now, so this trick will turn out to be useful and have some interesting physical interpretation later on. Now, we need a small definition and a big theorem that I'm not going to prove. So the definition is that given a matrix A, okay, sure. I'll just go to a new blackboard. So now a definition that we'll need is that given such a square matrix A, people define what's called the spectral radius of the matrix, which is so given A, we can define the spectral radius of the matrix, which is essentially the magnitude, the absolute value of the biggest eigenvalue. So this is defined as the maximum. It's a real number, and you just scan over all the eigenvalues, and you take the max of the absolute value of the eigenvalues, and that defines the spectral radius of the matrix. And then there is a strong theorem that is very useful for this development, but it's actually a heavy theorem that its proof is not very important for these applications, and it's quite heavy. So I'm not going to prove it. This theorem is due to the Gelfand, and surprisingly, it's used a lot in these physical applications. So there is a formula to compute the spectral radius of a matrix. And the idea is that you take the norm of the matrix to some power, and then you take the limit where this power goes to infinity, which is not entirely surprising, because when you take a matrix to a very high power, it's dominated by the largest eigenvalue. The surprising thing about this theorem is that it doesn't matter which norm you use. It's true for any norm. Like the norm of the vector, it could be anything you want. It could be like a sum over this any norm of that sort, and it would still be true. So it doesn't even matter which norm we use. That will be important for what we need. So this is a non-trivial theorem, but we won't need its proof. It's not very important for what I want to say. Okay, so now I want to show you the crux of the matter of how to establish the existence of such an eigenvalue, and how to show that the ground state, I'm using physical terminology already, like the largest eigenvalue is positive. So let's cover the proof. So you, by definition, well, let's take the largest eigenvalue. let's take the largest eigenvalue. And a priori, the largest eigenvalue is not even guaranteed to be the largest eigenvalue in absolute value. Is not even guaranteed to be real. So there is some eigenvalue which we can call lambda max, such that its absolute value is given by the spectral radius of the matrix. That's the definition of the spectral radius for finite matrices. So we pick that eigenvalue, and we denote the corresponding eigenvector by psi. So this is going to be the eigenvector for that largest eigenvalue. And now the trick is to define a new vector, which we will call psi twiddle, whose components are just the absolute value of the components of the true eigenvector.
But why is it clear that there is a unique eigenvector?
It's not even clear that it's unique. There is at least one such eigenvalue whose absolute value is equal to the spectral radius of the matrix, right? Okay, so we need to, so the idea is to define this psi twiddle I, which is now a real eigenvector and also positive eigenvector. Well, it's non-negative. I haven't yet proved that it's positive. So far, we just know that psi twiddle is non-negative. And then we just do the following computation. We compute the ith component of the matrix applied to psi twiddle. And, well, this is the same as the sum over j of a, I, j, absolute value of psi by that definition corresponding to the max eigenvalue that we assumed exists. And then we need to put j here. And then we put an inequality sign. And we use the triangle inequality. Since all the matrix elements are by definition positive, we can put the absolute value outside at the price of putting an inequality. And, well, so we remove the inequality. Then when A acts on psi, we know what we get. So we get the absolute value of lambda max times psi lambda max. And that is, by definition, the same as the spectral radius of the matrix times psi twiddle I. Is that clear? Okay. So, okay. And now, now we have this we have this interesting inequality. And now what we do is that we apply our trick. We have two vectors now that satisfy a weak inequality. So we can multiply them by the matrix A and turn the inequality into a strong inequality and even stick some epsilon. So we do that. Let's do it once. If we do it once, we get a right? There exists such an epsilon. So you can continue. You can continue in that way, and you arrive at the following formula. You just continue to apply the same result, and you arrive at the following formula. That this is a. Well, I actually don't even need I could even use that slightly weaker form. So you get the following result: 1 plus epsilon, then the spectral density to the power n, and then a psi twiddle. So you just do it n times, and then you use these inequalities to reduce, to apply them successively, and then you get this power of n. But now we're very close to a contradiction. Because according to the Gelfand theorem, we should be able to compute the spectral density from the norm of the matrix. Now remember that the norm of the matrix is defined to be like that, where you take the supremum over all the possible. This is too small. So the norm of the matrix is defined to be the supremum over all AX divided by x in any norm that you like. Okay? Or over all the x's that are non-zero for the sake of this being well defined. So this is very close to a contradiction. And in
there will be a power on the right-hand side, a to the n.
right, but then you use these inequalities to further remove the a's until you get to this formula. So now we're very close to a contradiction because applying this formula for a psi, we see that the spectral density of rho of a now satisfies a bizarre inequality. Okay, that cannot be true. Yeah, possibly. I possibly made a small error here. Yeah, you're probably right. So, right, thank you. So this is a contradiction. So contradiction to what? What did I presented the argument in a slightly confusing way. So what is this a contradiction to? Let's see if anybody is following. Exactly. Remember, in our small trick, there was a small footprint. So therefore, psi lambda max is real and positive, and therefore lambda max is real and positive. Now you have to prove that it's unique. It's almost trivial. Anybody could do it in a half an hour. So you could prove it that I could present the argument, but I feel that it would be a slight waste of time. So you could also show that it's unique. Okay. So this theorem is relatively easy. I just did it on the blackboard in, I don't know, like 10 minutes. Then there is a generalization that was actually what we're gonna need. And the generalization is very hard. It's a small generalization, but it actually turns out to be hard to prove. So I can't even, this is a generalization. So this is called the Perron theorem. This is from like 1909, maybe, something like that. This is Perron. And then there is a question that is omnipresent in this literature. What happens if the matrix is not, strictly speaking, positive, but just non-negative? The question is, what happens if this is true? What can we say? If the that's actually what's going to be important for the various physical applications we'll discuss, because A will be the Hamiltonian, and there will be some conserved charges. So the matrix would actually be block diagonal, and there will be lots of entries that are zero. So to use these theorems in a useful way, we need to be able to say something intelligent about the case where A is non-negative. So the generalization appeared like 30 years later by Frobenius. And he essentially, he essentially argued, proved. He proved that all these things all these great things that we've shown before, somewhere here. All this, well, where were they? That it's unique. Where did I put it? It's hidden somewhere. Oh, it's here. Yeah. So he essentially showed that this is that this, and this are all still true. So everything is still true. But only under the condition that some power of the matrix is actually strictly positive. So there needs to be some power of the matrix that is actually strictly positive. Okay? So you could imagine like a matrix like that. Then a matrix like that wouldn't satisfy that condition, and therefore, the eigenvalues don't have to be strictly positive. The largest eigenvalue doesn't have to be strictly positive or unique. But if some power is strictly positive, then you can rerun the whole argument with a little bit of work. Okay, so this finishes the small mathematical introduction, and you'll see how this plays out. I mean, this is already kind of reminiscent of physics. This will imply that you have some ground state which is very, very entangled, very mixed, and you'll see that this has implications for the uniqueness of that ground state. This is, of course, the uniqueness of the ground state, and this will also have some implications for the quantum number of the ground state. So all these elements will be used very heavily next. Are there any questions about the linear algebra theorem?
You mean the state satisfy the state with this eigenvalue is unique?
The what?
I mean, what do you mean by unique? You mean the eigenvector is unique?
The what unique? Say again? I don't understand the word that you're saying.
Eigenvector, the state with this eigenvalue is unique.
So eigenvalues have multiplicities, could have multiplicities, right?
No, what's the meaning of unique here? I didn't follow you. What's the unique here?
That this eigenvalue has multiplicity 1. I just mean that this lambda max is a multiplicity 1 eigenvalue. So there is like only one eigenvector. The geometric multiplicity is 1, and also the algebraic multiplicity is 1. There is only one eigenvector with that eigenvalue, okay? And it satisfies this positivity. So you can just play with some 2x2 matrices, see that it's actually true. Right, so it's a basis-dependent statement.
For the case of the Hamiltonian, what are the components of psi I in the energy basis?
Well, you'll see now. And it actually, I mean, some things like that may actually appear naturally when you do a Hamiltonian truncation. So now we'll construct some model, which is essentially the model for, it's essentially the quintessential spin chain model, which you can analyze using this theorem. So even though we cannot diagonalize it exactly, we can say many things about it exactly, non-perturbatively, so to speak, by using that result. So the model consists of L points. So there are degrees of freedom. This is a lattice model. And then we'll take the continuum limit.
Sorry, I have a question. So I'm confused. You mentioned some issue about symmetry. You said, well, you cannot apply Perron because there's symmetry.
Yes.
So I'm confused on two counts. First of all, I mean, if there's symmetry.
Yes, you're right. Yes, you're right. You're right. I misspoke. So the typical Hamiltonian that we'll discuss is block diagonal. So there are lots of zeros here, of diagonal zeros. And so that's not going to help.
That's not going to help.
But even because of the quantum field theory, or the lattice model is local, also that has lots of zeros inside. And so from those zeros, I'll be able to get rid of. And then we'll prove some theorems about the blocks. And then about those, we won't mind very much. We'll just solve each block, and then we'll compare the blocks. Yeah, thanks for I just misspoke when I said that thing. Okay, so the model consists of L degrees of freedom, where the label will be I, this will be 1, this will be L, and there will be an identification that whenever you see a formula where L plus 1 appears, we'll interpret L plus 1 to be the same as 1. So it lives on a circle. So it lives on a circle. Okay, and now we need to write what is the content of the degrees of freedom on each site. So and that, for the applications that we'll discuss, we'll take L to be even. Okay, so the content of each site is some spin. So each site has a spin degree of freedom. So it's not moving anywhere. It's just like an arrow, a quantum mechanical spin. So it's a quantum mechanical spin. It's an SU2 spin. People have, of course, you could put, of course, any Lie algebra you want at any given lattice site, but we'll discuss SU2. So it's some SU2 matrix. So the operators at each site are SIX, SIY, and SIZ, where X, Y, Z are the three generators of SU2. So they satisfy the standard SU2 algebra side by side. And you need to pick a representation. We need to pick a representation of SU2. That will determine the size of the Hilbert space and the actual Hamiltonian that we need to diagonalize. But we'll make this choice later. You'll see that there are some crucial differences between some representations, very surprisingly. So the Hamiltonian is that of an antiferromagnet. So the energy of two spins being aligned is actually minimal. If two nearby spins are, maximized. If all the spins were aligned, you would have paid a huge amount of energy. So there is a plus sign here. And you sum over all the sides, and you just take the spin at the I side and dot it into the spin in the I plus 1 side. And that's it. Okay, this is the model. So you need to pick a representation to make it concrete. And you can ask, does the answer depend on the representation? And it does so crucially. And one of the things that I want to explain is the dependence on the representation and how quantum field theory mirrors that funny dependence on the representation. So the physics of this model depends on the representation. And this is a 1 plus 1 dimensional spin chain. It's called an SU2 chain because the matrices here are SU2 matrices in some representation. And let me just tell you some historically interesting fact.
Sorry.
Yes?
Write your indices a bit bigger here.
Say again?
Can you please write your indices a bit bigger?
Oh yeah, sorry. Is it more visible? Is it visible now? Yeah. So this model is basically something that appeared in many, many different applications. It's a quantum antiferromagnet. And the first person who, I think, realized that the answer depends very strongly on the representation was Duncan Haldane, for which he got the Nobel Prize a few years ago. Okay, so now we'll study this model. Oh, yeah, this board doesn't move, so maybe I'll just erase the first board. Okay, so as you see, the statement that I proved before from linear algebra was basis dependent. So we'll try to search for a basis where this Hamiltonian is subject to that theorem, and we could apply that theorem and see what are the consequences. So the basis, what is the most familiar basis? So there is a trick that comes into choosing the right basis, and I don't know how people arrived at that trick, but this is a very clever trick. But once you realize that, everything follows very smoothly. So what is the most convenient basis that we know? Just choose some, well, we just diagonalize SZ, right? We just diagonalize SZ. And this is in the two-dimensional representation. So here I'm assuming for a second that we're studying the two-dimensional representation. So to have an intuitive feeling for many things that we're going to say, let's imagine that we're doing the two-dimensional representation of SU2, the spin up, spin down. So then, I mean, if this is the ice side, then this would be, of course, a half times the same thing. I'm just setting conventions now. This would be minus a half times the same thing. And the action of the other operators, well, let me just write the action on the up on the up spin, the action on the down spin follows from de Pauli matrices. So I'm just setting some conventions here. So this spin gets reversed. You can infer the action on the down spins by doing it twice. So I'm not going to write it separately. And the other one, my convention for that one is going to be that it has a plus sign here. So it's I over 2. And then the spin is reversed. Okay, so this is the most familiar basis choice. And strangely enough, there is a better basis choice. So what is the theorem that we want to prove? I'll phrase it as a theorem, but you can. It's just a fun fact about this model.
So you already picked fundamental representation.
Yeah, so this is for the two-dimensional representation.
I thought you said that you want to show that the answer depends on representation.
Right. I'm just giving here an example. Let's suppose you could put it on the computer. That's how you would implement it for the two-dimensional representation. Yeah, for higher representations, you know, there will be different matrices. So this is the two-dimensional representation. And okay, so what is the main result? The first main result that we want to prove. So this is like the first main result about this model that we'll need. So the ground state is unique. This is independent of the representation that we pick. This is always true. And this is true as long as L is finite. We'll discuss the continuum limit, of course, much more when we get to CFTs and Bootstrap and stuff like that. So the first theorem is that the ground state is unique. It's not often that you can prove such a thing about such an interacting model from pure thought, but here it can be done using these theorems from linear algebra. So step one. Step one in the proof is to construct a basis where the Hamiltonian is the off-diagonal elements in the Hamiltonian all have the same sign. So we can use the Perron-Frobenius. And so the convenient basis turns out to be the usual basis. So we need to pick a basis. So we take the basis to be the usual one, meaning the one that diagonalizes as Z. But we need to dress it with funny phase factors. So we need to dress it by an exponential of I times the sum over the odd lattice sites of SZ I. So let me just give you an example what that means. Oh, I forgot to write a pi. I pi. So let's compare the usual basis. Let's say that L was 2. L is 2 is something you can solve on a piece of paper. L equals 4 probably requires a computer, but it's a fun exercise to do anyway. So if some of you are, I wanted to mention that, if some of you like to do numerical experiments, try to do L equals 4. L equals 2 you can do analytically. You would see that many of these things come out very naturally. Yeah. Say. Yes, L is even. Yeah. So the usual basis, let's say I want to just show you the meaning. I want to give you an intuition for why this is a good, this strange looking basis is good. So the usual basis, let's say for L equals 2 and spin a half would have been up, up, right? Up, down, down, up, down, down, right? That would have been the usual basis. But they're saying no. Let's pick the following basis. So every time the odd spin is up, we put an I. And every time the odd spin is down, we put a minus I. But this overall I doesn't matter because it's just a linear transformation. So basically, the first two vectors remain the same. but the other ones pick a minus sign. Okay, so now we have this basis. Just differs by signs from the usual basis, but the signs will turn out to be crucial. So the claim is that in this basis, all the off-diagonal components of the Hamiltonian are non-positive. So we're not quite able to use the Frobenius-Perron theorem, but we're getting close. So this is a point where it would be, okay, it's premature to make this comment. Okay, so all the off-diagonal components of H, all the off-diagonal entries of H are non-positive. So now I want to describe a little bit the structure of H in a little bit more detail. I want to get more into the physics to describe the conserved numbers and what is the general structure of the Hamiltonian here. And then we'll see that this comes out. Okay, so just to develop some intuition, let's think about this case where L is just 2. The Hamiltonian is S acting on the first spin and multiplying S acting on the second spin. So what are the off-diagonal? This is some intuition, okay? Before we get to some general statements, let's develop a little bit of intuition of what this Hamiltonian does in the 2×2 case. Sorry, in the case that the Hilbert space is 4-dimensional. So in that case, well, we can always write H as Sx, Sxi, Sxi plus 1. The indices should be bigger. I plus 1. We can always write it like that. This is just this is the same as what we had before. And then we have the Sz part, but we can ignore the Sz part because the thing that I want to show now is that the off-diagonal elements of H are non-negative. So we can ignore Sz because Sz is diagonal in this basis. So we just need to discuss these guys. Now, looking at this basis, we see that if we act with this operator on something that looks like up, up, suppose you have something that looks like up, up, then this cancels out because this guy reverses this spin, this reverses the other spin, this reverses the first spin, and this reverses the first spin. But in one case, we get a factor of a quarter with a plus, and in the other case, we get I/2 times minus I/2. Yeah, we get I/2 times I/2. So we get a minus a quarter. So on these guys, we get 0 if we apply this operator. And the same is true for when these two spins point downwards. We get 0 because the first piece cancels the second piece. So you should just check these things at home. But if we act on up-down, let's say, then these two terms combine. So they have the same sign. And they turn it into down-up with a plus sign. And vice versa, if we acted on down-up, they will turn it to up-down, again with a plus sign. And that's why it's crucial to have these minus signs here. Because up-down goes to down-up. So if we want to make sure that the entries of the Hamiltonian are non-positive, we need to stick some minus signs here. So that explains why we need to address the odd spins by this factor. That would guarantee that the Hamiltonian is like basically negative. Okay. So more formally, so on this guy, after we act with this operator, we get down up with a factor of maybe 1/2. Okay, which you can check. With a factor of 1/2.
Perhaps it would be easier to think of that as 1 minus the permutation.
Right. Very good. Indeed, it's useful to write it as 1 minus the permutation. However, what I'm saying here is true for any basis. The statement that the Hamiltonian has no negative entries is true in any basis. Okay. Not just for the spin a half. Oh, I meant any representation of SU2. Yes. Sorry, I misspoke again. Okay, so why don't we care about the diagonal elements? Why did I concentrate on the off-diagonal elements? Well, and why are we talking about non-positive rather than non-negative as before? So the non-positive versus non-negative is obvious. Previously, we were looking for the largest eigenvalue. Now we're looking to minimize the Hamiltonian. So we just apply Frobenius Perron with a minus sign. But why can we ignore the diagonal elements? Does anybody see the argument? So the Frobenius Perron theorem was stated as a theorem for positive matrices. But actually, it's not necessary. We don't care what sits on the diagonal. So the Frobenius Perron theorem was stated for matrices that satisfy that. But actually, it's not necessary. You can put whatever you want on the diagonal. It would still be true that the largest eigenvalue is real, and that as long as the off-diagonal elements are positive, it would still be true that the largest eigenvalue is real, and that the largest eigenvector is strictly positive. Why is that still true? Because if a matrix is positive everywhere, okay, suppose it's completely positive here, and you have whatever you want on the diagonal, you can always add the unit matrix. And then you're in the realm of Frobenius-Perron, and the unit matrix doesn't change the eigenvectors, doesn't change the fact that they are strictly positive, doesn't matter for anything. Okay, so to apply Frobenius-Perron, we don't need to worry about the diagonal. That's why we're happy discussing the off-diagonal elements. Okay, so H has non-positive off-diagonal elements.
So the overall sign of the Hamiltonian was not important.
Well, if I put a ferromagnet rather than an antiferromagnet, then Frobenius-Perron would allow me to search for the largest. Well, I'm trying to minimize the eigenvalue. If I put a minus sign, the interpretation of the thing that I'm doing would have been to find the most excited state, which is physically uninteresting. So ferromagnets cannot be treated in this way.
Why? You shouldn't just change the basis and then you can change the ferromagnets as well. So for antiferromagnets, you do this trick with heading phases, but what about doing ferromagnet and not changing the basis? Then it seems like it doesn't work.
Yes, I agree. It would still work.
The basis completely.
Yeah, yes, yeah, I think you're right. In the other basis, it would still work. Yeah, I think you're right. It's a good comment. So H has to be so we've argued that this is true in this weird basis. The next step is that I wanted to explain how H looks like in more detail in this basis. So there are actually conserved quantum numbers. What are the symmetries of this model? Let's see if somebody is still awake. What are the symmetries of this model? That would allow us to classify the blocks. So what are the obvious symmetries of this model? There is translation. That's what you're showing? So there is translational symmetry. That will be very important. In fact, one of the reasons that I'm showing you this whole thing is that perhaps you thought that translational symmetries of the lattice correspond to translations in the continuum limit. You'll see that this is not true. But we're not yet there. I'm jumping ahead. That's one of the messages from this theory. So there is a translational symmetry. So yeah, we'll eventually use it, but not now. What other symmetries are there in this model? Yeah, right. So there is SU2. So we can diagonalize this. This is the generator of SU2. This cannot be changed by acting with the Hamiltonian. So we have blocks. Okay, we have these blocks. Let's say here, let's call this thing the total magnetization. This is usually called the total magnetization. So this is like the m equals 0 block. This is the m equals 1 block. Typically, the magnetization can be also a half integer. But since I require that the total number of spins is even, it's always an integer. The total magnetization is always an integer. And it continues, so on and so forth. So the Hamiltonian has this block diagonal form. And no power of the Hamiltonian will be strictly negative. And we don't care what's on the diagonal. We have already agreed on that. Now, even within each block, the Hamiltonian does not act faithfully, because it's a nearest neighbor interaction Hamiltonian. So it's easy to imagine. You can just play on the computer with the four sides model, and you'll see that the Hamiltonian does not act faithfully even within these blocks, because it's a nearest neighbor interaction Hamiltonian, and it cannot take any state with given magnetization to any state with given magnetization. A hard technical theorem is that there is some power k depending on the block for which it becomes faithful within each block. So this is an exercise for you. It's not terribly hard to show. Yeah.
So let's look at m equals 0 block. It's m equals 0, but it can be m equals 0 state of a representation.
Great. I'm getting there.
So
Fantastic.
That has to do with locality, right?
Correct. But just from locality, you know that it's not going to be faithful within each block, because there are lots of states with magnetization 1. You're not going to be able to interpolate between any state and any state with one application of the Hamiltonian. Maybe you need many applications of the Hamiltonian to be able to get to any other basis state.
Since we are about symmetry, I thought that the first one was
Right. Symmetries imply this structure.
More than that.
Even more than that, because some states here have to have degenerate energies. Symmetries imply a little bit more than this. But even that is not enough. You need to, I want to show that, well, I won't be able to show it now, but it's not a hard exercise to show that sufficiently large powers of the Hamiltonian become faithful in each block. People convince themselves of this by numerical, just playing it with it numerically, but you can prove it also. It's not too hard. Okay. So now we can use Frobenius Perron in each block. What does Frobenius Perron imply in each block? It implies that there is a special wave function psi m, which is the lowest. So we can put it in like this. So there is some special wave function in each block with energy that depends on m a priori, and that it has completely positive coefficients in terms of our basis. So we can write it like this. So there is a wave function with totally positive coefficients in our basis. And the energy depends on m. And now the next step, when did I start? I forgot.
Not sure.
Oh.
But just take the identity.
This is the
At the identity.
But you started definitely 20 minutes later.
Okay. So I want to drive home today at least one important result, a very important result, that the ground state is unique. It has spin 0, and it's a positive combination of the basis states. This is like one of the only examples where we can prove such a thing. And then next time we'll see that this has far-reaching implications for conformal field theories. So this is true by Frobenius Perron But now we need to minimize over M. We don't a priori know which of these guys will have the lowest energy. But here there is a point that needs to be remembered that Slava already brought up, that we haven't used SU2. So far we just used the fact that this is conserved. So now we have to think about what are the implications for SU2, implications of SU2 for these blocks. So let's make let's ask the question: could it be that we have to ask this question in an intelligent fashion? We have to ask what is the Casimir of SU2 acting on the true ground state equal to. So there are two logical options. This is the SU2 Casimir. There are two logical options. Maybe there is no unique answer for what is the true ground state as a function of M. If the true ground state has some SU2 spin, then there will be, then it will be the same in this block. You know, if it has some SU2 spin 1, let's say, then the spin in this block, so the energy in this block, in this block, in this block would be all the same by SU2 invariance. So it could be that E of M does not have a unique minimum, and this is if and only if the spin of the ground state is non-zero. Is that clear? If the spin of the ground state is non-zero, this Frobenius Perron wave function would yield the same energy in several different blocks. However, if the spin of the ground state is exactly vanishing, then this will be the unique answer. Is this clear?
Could you repeat that again?
This is a hard argument. Can you tell me what part, like, there is a divergence of what I said and what you understood?
Yeah, what was the role of the Casimir? I guess.
So we have this. Did you understand
Yes.
Are you okay with the construction of the positive wave function? I haven't even used it. It's positive yet. It's going to come. So we have some ground state in each block, which is unique. We know from Frobenius Perron, and we know it's even positive. Then we have an energy that is associated to that ground state that is a function of the total magnetization. Now we should ask, which is the true ground state? So we need to scan over all the possible total magnetizations and find the true ground state. There are several options. There are two logical options, since SU2 is a symmetry. One is that the answer is that only M equals 0 is the ground state, and that immediately implies that the Casimir of the ground state has to vanish, because if it did not, there will be some lower energy state here, some higher magnetization. And the other logical option is that the ground state is not actually unique, so it's degenerate. So this is the question of degenerate versus non-degenerate. It's the same question as what's the Casimir. Because of Frobenius Perron, the question of degenerate versus non-degenerate is the same as the question of what is the Casimir of the ground state. It's only because of Frobenius Perron, otherwise it's not the same question. Okay. So so if the Casimir is 0, it's non-degenerate, and the spin must vanish. And if it's degenerate, the spin cannot vanish, and it's 1-to-1. Is it clear or not so much? Well,
when it has some spin, the ground state would have support only over a few blocks, right?
Over some finitely many blocks.
Yeah.
Right. So if the ground state has a non-trivial SU2 spin, it will have to have support over a few blocks. So the true ground state would be some, there will be a multiplicity. Okay? Is it still shaky or?
I'll ask you later.
Okay.
It seems that you're saying that if the ground state is degenerate, then this degeneracy can only be true due to symmetry.
That's because, and this is what Frobenius Perron buys you.
Because of Frobenius.
And this is already getting close to QFT. Now you see? Because in QFT, we often think that degeneracy can only be due to symmetries. So this is a case where you can make it absolutely precise. Okay. So this is, okay, I won't repeat this point anymore. Oh. This is an immovable board. So we'll go here. Okay, so
I thought that when you argue that orthogonal elements of Hamiltonian are negative,
Right. That was when the full matrix is negative. But here there are lots of blocks with zeros, which cannot be circumvented by raising the matrix to some high power. They will remain. Frobenius, this statement that there is a unique ground state with positive entries is true when the full matrix is, let's say, negative or positive. But when there are zeros, it doesn't apply. However, in these blocks, there are no zeros for a sufficiently high power of the matrix, so it does apply. Okay? And from this logic, you infer this conclusion that Slava nicely summarized, saying that the degeneracy is in one-to-one correspondence with symmetry breaking, that the ground state is not SU2 invariant. So how do we show that that the m equals 0 is the only minimum, is the true minimum? So how do we show that? I really encourage you to do a numerical experiment with 4 spins or even 2 spins to see that this is true. So the argument for that is quite nice. I'll tell you the argument quickly, and then you have to meditate over the argument at home and see that it really establishes what I said. So this argument would use that fact. So let me show you the proof of this. The proof that the spin is 0 and there is a unique honest-to-God ground state. So the idea is that let's consider, just for a second, a different question, a different Hamiltonian, which is constructed in the following way. You take all the odd spins, you add them up, you get a vector, right? You just take all the odd spins, add them up, you get some vector, which is well, the total combined spin. And then we do the same for the even spins, and we consider this Hamiltonian. Okay, this is a much, much simpler problem. You can think about it as coming from, so this is a conserved quantum, this is a conserved, this is the total Casimir. So if we expand that, we get the Casimir of the even guys, the Casimir of the odd guys, and then this spin-orbit coupling, so to speak. So if you remember that when you do spin-orbit in quantum mechanics, you get a mixed term like that for the internal spin and the orbital spin. So this funny Hamiltonian has the same symmetries. It's easily solvable because it's given by just the algebra of the Clebsch-Jordan symbols. It's not there is nothing deep about it. And amazingly, it also obeys the same property that all the off-diagonal elements of H are non-negative. So it obeys the exact same properties, the same property that all the off-diagonal elements are non-positive. I mean, that's true, and then there are these blocks, where within these blocks you can raise the H-twiddle Hamiltonian to some power, make sure that it covers all the basis states. So H-twiddle is an easy problem, a trivial problem, you could say, for which it's just a spin-orbit coupling between two non-interacting spins. And for that guy, the same conditions are obeyed. Okay? And therefore, the same Frobenius-Perron theorem can be applied. But now we know the answer for what is the true ground state. How do we minimize this scalar product? So we minimize it by taking these two guys to be the largest they could be, and this could be the most negative it could be, so that the whole thing is 0. So this is bigger or equal to 0, right? So minimizing this piece is like putting the even spins all up, the odd spins, putting the even spins in the maximal possible symmetric representation, putting the odd spins in the maximal possible symmetric representation, so that this has the biggest possible Casimir, and then these guys are in the singlet state. So you make the even spins have the largest possible spin possible, L over 2. The odd spins are also in an L over 2 irreducible representation, and then you take the product of these two spins so that they're in the singlet state. And then this whole thing vanishes, because the whole thing is a singlet, and this is minimized. This is like minus L over 2 or something. Okay, so we minimize it by putting the whole system in the ground state where the Casimir of this wave function is 0. So we know how to solve this problem. It obeys exactly the same conditions as before, but here we know that the true ground state has 0 spin because I've just constructed it for you. And we know from Frobenius Perron that this is positive. Okay, what does it mean? Yeah.
Why did you have to put all the even spins in the highest possible symmetrical?
So I want this product to be the most negative it could be. How do you make it the most negative it could be? You take this to be the largest positive it could be, largest positive it could be, and then you take this to cancel them exactly. Okay? So you put all the even spins in the biggest representation they could be, the odd spins in the biggest representation they could be, and then you combine them into a singlet state. So you can check it numerically. So we know the solution of this problem. The true solution of this problem here is that the ground state is non-degenerate and spinless. And it has quantitative coefficients by Frobenius Perron. And now comes an amazing trick. Since both ground states have only positive coefficients in the same basis that we've constructed, their overlap cannot vanish. Right? So the ground state we've constructed here, psi 0, for this block, must have non-zero overlap with this ground state here, because they both have positive coefficients. So there cannot be cancellations. And therefore, this has to have 0 spin. And that's it. And we're done. Okay? So this proves that the ground state is unique. Are there any questions about this trick? It's a nasty trick, but I mean, you could try to check it numerically. You can also try to construct, I mean, maybe a more educational way of doing that. I mean, this seems like an extremely ad hoc trick. Like, how could you possibly think about it? I think a more productive approach to this problem would have been to construct the spinless combination of the basis vectors here, the one that has 0 Casimir, just construct them numerically or analytically, and show that they have positive coefficients in our funny basis. Indeed, say that you had 2 spins. How do you construct the spinless ground state? You remember this mind signs? This is why it has positive coefficients in our basis. So this basis that we've constructed with the funny minus signs, a posteriori, we can understand that it's such that the spinless ground state has positive coefficients. So a more productive approach to this problem would have been to construct the spinless ground state here, the one with 0 Casimir, and notice that it has only positive coefficients in the funny basis. And then we would have been done, because then they must have some overlap. Okay, so this is like a nested trick that achieves the same thing without constructing that state explicitly. I guess to construct it explicitly is quite a bit of work, because you need the Clebsch-Jordan coefficients for multiplying 2 huge representations. So it might be easier in this way, but it's not very, it seems like a magic trick. You say again?
You're restricting to translation invariant states?
No, I haven't used that yet at all.
But then you still have zeros that don't go away even if you take powers inside the block. Different momentum states don't talk to each other.
Right. Say again, what are?
Are these blocks, do these blocks have well-defined momenta, eigenvalue in the translation?
Oh, you're asking within each block? You could, so another conserved number in this business is, of course, the momentum, the discrete momentum. And you could say that you label the blocks by the 2 quantum numbers. And then you could, you could try to repeat the same process for the momentum quantum number, proving that the ground state has 0 momentum. You could do that if you wanted. Say again?
You don't need to, I mean, your basis vectors do not have definite momentum, they just have definite n.
Right. I'm just saying that if there are additional conserved quantum numbers, the Hamiltonian would be diagonal in both.
Yeah, but I'm saying that about Perron's question, the momentum doesn't seem to be relevant for this argument.
That's correct.
But if you don't specialize the momentum, then these blocks are zeros, which don't go away with powers, just because it's protected by symmetry. Powers of the Hamiltonian will still have zero inside the block.
No, this would be true if the basis vectors were eigenstates of momentum.
Yeah.
No. So your objection to that.
Yeah. But in principle, you're right. If there are additional conserved quantum numbers that we didn't discover, it would hit us in the face because then when we raise the Hamiltonian to some power, we won't be able to cover all the basis states. Yeah, so the momentum quantum number would not allow you to get some funny linear combinations. But okay, we don't need that. We just need that the individual terms are. That you can get any. All we need is that there are entries all over the place. So here, we don't need that you can get any linear combination starting from any given vector, right? Okay. Now the second step. So this is part one of this very interesting story.
So far, everything would also be true for ferromagnet.
No, for the ferromagnets, for example, at zero temperature, they don't minimize the magnetism. So the magnetism is like at the maximum. So it's not going to be the same.
So what
Because this is an anti-ferromagnet, so classically it wants to be like spin up, spin down, spin up, spin down. So the magnetism goes to zero.
what goes wrong in this proof?
Everything is not true. It's not like. I mean, it's like a completely different problem, you know? It seems like a sign flip, but minimizing a matrix and maximizing a matrix is a different thing. I'm minimizing the matrix, not maximizing it. Okay, so we've shown something quite fun that is very rare in these many-body systems, and we've seen some glimpses of why this is related to quantum field theory. Now, the next result that I want to tell you